Okay, welcome everyone. This week we're delighted to have a seminar by Scott Armstrong from NYU, and he's going to tell us about anomalous diffusion for passive scalars by fractal homogenization. So Scott, take it away.
All right, thanks to the organizers for the invitation and the chance to speak in this nice online seminar. Please interrupt me if you have questions, because I also enjoy the interaction, even if it's just through the screen. So please don't hesitate. So I'm going to be talking about a work that is joint with Vlad Vicol. It's about anomalous diffusion and using homogenization to prove anomalous diffusion. And I'll say what that is in a second. No, I don't know how to use my controls. Okay, there we go. Okay, so what is the context of my anomalous diffusion? So we're studying the advection-diffusion equation. So I have a parabolic equation essentially with a small kappa amount of diffusivity. So there's a parameter kappa in front of the Laplacian, and you think of that as a small parameter. There's an advecting vector field B, which is dotting into the gradient here. So this is a drift term, which is of order 1. So you think that if kappa is small, this is almost in some sense a transport equation, and there's a small kappa amount of diffusivity perturbing that, if you want. It's very important that the vector field be incompressible. So it's divergence-free up here in the top right. I put that. So if it would not be divergence-free, then it sort of wouldn't be physical for the applications I have in mind. And so it's very important that it be divergence-free. Otherwise, it also makes the problem a lot easier if you're allowed to push things into have sinks and sources. So we're interested in the regime in which the vector field is rough, so not Lipschitz, but it's still going to be continuous. So it's not going to be completely crazy like white noise in time or anything like that. It's a function. It's going to be continuous. I'll say more about exactly how continuous in a second, but it's not so continuous that the ODE trajectories will have necessarily unique solutions. Okay, and so the vector field, we're trying to make a vector field that looks sort of like the velocity field of a turbulent fluid. That's the idea. You can tell me how close we got here at the end. And again, this parameter kappa is very small. So we're in the regime of sort of large Reynolds number because the vector field is rough, and large Peclet number because the kappa is very small. Okay. So this is called a passive scalar because it describes the density if you drop some ink into a fluid, how the concentration of the ink would spread, for example, or a pollutant or the temperature of the fluid and things like that. So the point is it doesn't affect the fluid itself. So it's kind of decoupled from the fluid equations themselves. They're just pushed by the fluid. Okay. So that is the setup. And before I say what anomalous diffusion is, I want to give a very basic estimate. So if you look at, this is sort of the basic energy estimate for this equation. If you have the heat equation, and you start with some initial data and you want to evolve it in time and you want to study how that decays to equilibrium, what you do is, and I should mention I'm on the torus, so everything is compact, there's no boundary anywhere. So if you had the heat equation, you would just take the time derivative of the L2 norm squared of the solution. So so for every time slice, you integrate the square of the scalar. The scalar has mean 0, and that's a property that'll be maintained by the PDE. So if it starts off with 0 mean, it'll always have 0 mean. So if you differentiate the time derivative of the L2 norm squared, it's like the variance of the scalar. And you find that by just one integration by parts, that the sort of drift term drops out, and you have just minus kappa gradient squared times 2. And so this says that the gradient squared, its integral, tells you the sort of rate of the decay of the scalar's variance. Okay. And if you integrate that, of course, then you see that the drop of this L2 norm squared is going to be equal to the time integral of this L2 norm of the gradient squared in time, integrated over space. And so you can call this thing, if you want, the dissipation of scalar variance. Okay. And you see there's a kappa in front here. So if somehow the solutions theta kappa, which depend on kappa, would be uniformly bounded in their gradient in L2 as kappa goes to 0, then this term would be a mo of 1, but there's a kappa in front, so it would go to 0. And you would see that in the limit, you would get a property of the transport equation, which is that LP norms don't decay. Because in this case, my transport equation is sort of advected by a divergence-free term, and so that means that the flow maps don't change the Lebesgue measure, so none of the LP norms would change, and so that's what you would expect if things were nice somehow. Okay, I think I just also sort of cannibalized my next slide. So yeah, so if B has enough regularity, the ODE trajectories are uniquely defined, and therefore you would expect the scalar as kappa goes to 0 to converge to a solution of the transport equation, which, if the ODE trajectories are uniquely defined, is unique, and therefore the whole sequence should converge to this unique solution. And this solution preserves LP norms, and so therefore you expect that the dissipation of the scalar variance goes to 0. And this is the case. This is what it would mean to not have anomalous diffusion. Okay, so anomalous diffusion refers to the situation in which that does not happen. There's a positive number rho such that this number here, this dissipation of scalar variance, stays bounded below. You expect it to be, of course, proportional to something involving the scalar, because the initial data, because it's a linear equation, and so you try to get it lower bounded by the L2 norm squared. That's what you'd expect. So this is what refers to anomalous diffusion. Okay. Again, stop me if you have any questions. I can give this a probabilistic interpretation, and this is well known. If you think probabilistically about the PDE that I wrote down, it's basically a parabolic equation with drift. And you can think of it equivalently as studying the trajectories of a stochastic differential equation, which is like thinking about how the particles are going to move under the diffusion. So I think I put the 2 in the right place. If I didn't, there's supposed to be a 2 somewhere. But the SDE is this one. There's this W is a Brownian motion. There's a constant depending on there's a kappa there. There should be a 2. I think there's a square root, and this is the amount of diffusivity. And then it's advected by this this deterministic term. So if this would not be there, then you would have just the ODE flow. And if this is there, then you imagine that if the ODE flow is nice, it would just perturb the ODE flow. And so if B was sufficiently regular, you'd expect, for example, that as kappa goes to 0, the variance at time t, here I'm thinking of t as order 1 or something, the variance of this in the position would be proportional to kappa. It would be kappa times t, in fact, or something like that. But maybe that doesn't happen. Maybe somehow, no matter how small kappa, even for very small kappa, the interaction of these two terms causes some spontaneous stochasticity, it's called. And that refers to the statement where you don't have this. In at least along a subsequence, the variance of this quantity stays positive. And again, I really mean for just think t equal to 1. I'm not trying to say anything as a function of t in this statement. So it turns out that these are equivalent. You can show at a qualitative level that spontaneous stochasticity, it's a probabilistic statement, is the same as anomalous diffusion for every initial data. So you have to have anomalous diffusion for every initial data, and then you can go back and forth. Okay, so this was proved by Theo Drevis and Greg Eink a few years ago. Okay, so that is the basic problem I want to study. Let's see if I can go to the next page. So the funny thing about this is you can ask the question, does there exist a continuous vector field exhibiting anomalous diffusion? And it turns out to be open. Now I should put an asterisk here because there have been some papers about this that prove anomalous diffusion. So I really mean, does there exist a vector field with the conditions that I like that exhibits anomalous diffusion? Some conditions that I'm going to put for admissibility of the vector fields that I want to see. And this is an open problem. And this is funny because this is a very basic, this should be a very basic thing that turbulent fluids do. So I went into this project knowing nothing about fluids, and so my co-author Vlad has been educating me, and I've been reading about it. And so the basic idea, as I understand it, in Kolmogorov's theory of turbulence, is that for very turbulent fluids, you have this parameter nu here is small, the viscosity, and if the fluid is turbulent, then you expect that this sort of analog to what I was calling the dissipation of scalar variance, this and I have brackets here because I'm thinking about this as the statistical kind of ensemble, but it means some kind of average. But if you look at the kinetic energy and you average it, then it should be O of 1, even for viscosity is very small. Okay, and this refers to anomalous. This is called anomalous dissipation of kinetic energy. And anyone who's begun to study Kolmogorov's theory of turbulence knows that this is true. I mean, the physicists think it's obvious. Maybe there are physicists in the audience that think that will tell me, yes, this is very obvious, but it's been experimentally verified, numerically verified, and it's sometimes called the zeroth law of turbulence. Of course, if you could prove something like this, then you could look at the first coordinate of u, and you would have it for the scalar equation, right? Like you can forget that the Navier-Stokes equation is actually that the velocity field is the solution, and you can. So this is a harder thing to understand than the scalar equation. Anyway, so physicists think this is obvious. Mathematicians, what can we prove? Essentially nothing about this. It's a big open problem to understand this. Now, why is that the case? This is a hard problem because the explanation of the physicist of Kolmogorov for why this should happen has been understood for more than 100 years, probably even longer. The idea is that this advection term, as long as there's there's either an initial condition with a lot of energy, or there's some maybe large scale stirring of the fluid or something that keeps energy in the system, then this advection term will develop many scales, and kinetic energy will somehow get passed scale by scale down into the small scales. So you think of, you're going to start off with very large wavelengths maybe, but then the interaction of this quadratic term will cause some of the energy to move into smaller wavelengths, higher frequencies. And you'll have this cascade going down, which will not stop until you get to the very small scale at which this diffusion term can erase it. And it can just destroy those modes. And then you'll have loss of kinetic energy. And so the total amount of kinetic energy that is being lost or whatever is O of 1, no matter how small kappa is or nu is. Okay, so this is the basic idea. So we want to have the more modest goal of trying to understand the passive scalar case. The passive scalar case is very analogous and is thought to have sort of similar properties for similar reasons. Yeah, so the point is that the passive scalar is a little more tractable because it's a linear equation. The thing that you want, I mean, there's still something nonlinear going on because you want to understand kind of how the large wavelengths, low frequencies get pushed into low wavelength, high frequencies. So you have to understand that somehow. But at least for the passive scalar, if you think about you're being given the vector field and trying to deduce properties of the scalar from it, it seems easier. Anyway, if we can't solve the passive scalar zeroth law of turbulence, maybe we're a bit lost for the full-blown thing. Okay. However, it is interesting in its own right because it is also physical. And in the early 50s, Korsun and Bukov independently made a kind of analog to Kolmogorov's theory of turbulence for passive scalars. So that was almost 70 years ago now. And a lot of the scalings that you have in Kolmogorov's theory are kind of mirrored in this passive scalar case. Okay, so here's a quote that I took from a paper of two of my late Courant colleagues, Marco Avellaneda and Andy Maida. Discussing this in 1994, they were essentially thinking about the same problem. They wrote a series of papers, also trying to use homogenization to understand the passive scalar problem for a large Peclet number. And they were explaining why it's physically interesting, not just a toy model for turbulence, and what's hard about it. And so here's a quote that from their paper. Maybe I won't read it. Okay, so now let me describe the previous results and what has been done on this problem so far. There is a model called the Kryknen model, and the Kryknen model is a special vector field, and where you just write down, you say the vector field B is a Gaussian field, which is white noise in time and has some kind of colored noise in space. And because it's a Gaussian field, Kryknen discovered that he could do exact calculations. You have a white noise field, so you can take expectations of certain moments, and then these equations close by magic, and you can compute things exactly. Okay, and using this, a lot of people study this model, and there's a paper. I should probably quote like 50 papers, but I'm actually ignorant, so I cannot. But there's this paper by Bernard Gawedzi and Kupianen 25 years ago, who proved anomalous diffusion or anomalous dissipation for this model for the passive scalar with this particular vector field. And this vector field is white in time, so it's not continuous in time. It doesn't look like a fluid. And the white in time behavior of the vector field, I think it cannot be relaxed. So that when you talk to people about this, they first tell you, oh, but that can be relaxed. And then they come back the next day and say, I tried for 2 hours, it cannot be relaxed. Because the white in time is essential for the closing of the exact calculations. But white in time is not very physical. And if you think about the model where you have this, this drift term, if you have a particle and it's being bombarded by a white noise vector field, it starts to diffuse just because it almost acts like a forcing. And so it's not that anomalous, maybe the diffusion in this model. So it's not, real fluid doesn't look like that. In any case, if you make the thing really noisy in time, then you can get diffusion, but it's not clear what that is actually telling us. Okay, so fast forward to a few years ago, this paper came out by Theo Drivas, Ogindi, Iyer, and Zhang in 2019 on the archive. It was published in 2022. And they constructed the first real example in some sense. They made a vector field, which they wrote down exactly. It's deterministic. It's made out of basically periodic shear flows that alternate between horizontal and vertical shears in 2D. 2D is harder, actually, not easier. So the lower the dimension, the better. So anyway, they make a 2D one. Their field is almost Lipschitz continuous. So this epsilon is very small. They can make it as small as they like. And they're L1 in time. The vector field is actually C infinity away from t equals 1. But at t equals 1, there's almost like a self-similarity blow up happening. So on the whole unit interval, it's only in L1. And from the point of view of the diffusion anomaly, sort of nothing happens until suddenly at time 1 there's an explosion of if you graph the L2 norm of the scalar, it'll be for a very small kappa, it'll be essentially constant, and then drop down, lose a factor of 2 in the last nanosecond. Okay. So again, they have this switching in time very, very quickly in time, which allows them to and as the switchings, as things start to switch in time, the amplitude of the vector field goes up so that it's only in L1. And then they have diffusivity at the last second. So let me say a little bit more how this happens. Basically, what they do is they find a vector field, which, if there would be no diffusion, would take a checkerboard like this in time 1/2, turn it into a checkerboard like this. It just rearranges the checkerboard squares so that this pattern goes to this pattern. Exactly. And then they repeat it, but they scale down the vector field by a factor of 2, and they scale up the amplitude by a factor just less than 2. And in time 1/4, it looks like this. And so they keep repeating that on these little dyadic intervals. The checkerboard squares get smaller and smaller and smaller and smaller. You imagine the solution is 1 on the red squares and 0 on the black squares. Okay. So the diffusion is barely doing anything. Like maybe it's so because the vector, so the vector field is doing this, and the diffusion is not. It's maybe rounding these edges a little bit, but it's kind of irrelevant until finally you get down to a small scale at which the checkerboard, which happens in time 1, because if you sum these numbers, you get 1. But you get down to a small scale at which the diffusion can suddenly smear out all the checkerboard squares and turn this thing completely one color. in the last second. And that happens in some time interval, which is of size kappa around 1. I think it may be size square root kappa now that I think about it. But anyway, it's some very short time around 1. So this is the first example, which is great, but it's still not maybe super physical. There's been other works that are sort of based on this construction. And these are preprints last year. And there are more than this now, actually. But we have Colombo, Crippa, and Sorella. They essentially take the same sort of checkerboard decomposition. All these papers are based on sort of this vector field, which is rescaled in time and having a blow up time at time 1, basically. But they also obtain uniform in time Holder estimates for the scalar, which is sort of in some sense, it's a harder estimate to prove, and it's very interesting. And the Holder exponent they get is what you would expect if you took the sort of Abukov-Corson exponents in that they get in passive scalar turbulence, and then tried to make an analogy to Holder regularity in the mathematical context. You would get the same exponent. We have Delilis and my autocorrect screwed this up. I'm really sorry. It's supposed to be Brue, B-R-U-E, but my autocorrect made it Bruce. Anyway, Camilo Delilis and Elia Brue, they put this advection-diffusion equation into the Navier-Stokes equation. What you do is you make a 2D passive scalar. You put the vector field in the first 2 coordinates, and you put the solution to the passive scalar in the 3rd coordinate. And then you notice that almost solves the Navier-Stokes equation. And you plug it into the Navier-Stokes equation, you see what the right-hand side is. It'll pop you out a right-hand side. And you can call that right-hand side a force. And then you can use that to then have, but then anomalous diffusion for the passive scalar is kind of anomalous dissipation for the Navier-Stokes equation with that force. So they did this, and they say it's like adding half a dimension. Anyway, in all these works, the basic mechanism is the mixing properties of the vector field. It takes the level sets of the initial data and puts them and smears them around until the level sets are so intertwined that the diffusion then smears them out. It just like creates scales by just smearing it around, which is what mixing is. And these results are only proof for special initial data. In fact, I don't even think it's true that for this vector field they have that it'll work for every initial data, because I think that due to the equivalence with spontaneous stochasticity, I think the trajectories of the vector field that the paths of the particles will be essentially deterministic as kappa goes to 0, except at the final time instant. And so I don't think it can make a big jump there. And so I think that actually it will not be true that for every initial data you have anomalous diffusion. Okay, so there are other works maybe that so these works. Okay, so there's a lot of other works that sound like they're very related to this, but actually aren't that related. There's a lot of papers that are based on mixing, but as I'm going to try to explain, studying the H-1 norm and saying that its norm decays very fast is not the same as saying that the L2 norm decays. And it's just kind of a different problem, and it doesn't imply the anomalous diffusion. There's been many works that try to use the homogenization point of view, which I'm going to explain in a second, and use it on this passive scalar problem. So it's not like we've invented that. I want to sort of underline that. This goes back even before these works that I referenced, but certainly in the 90s, people were working on that. However, there were no proofs of the anomalous diffusion. Okay, so now I would like to say a few words about what I would like it to see in the example. Okay, so ideally, in a perfect world, we would like to prove that the anomalous diffusion is happening when the vector field is maybe a solution of Euler or Navier-Stokes. So maybe it's a solution of Navier-Stokes, and the viscosity parameter in the Navier-Stokes equation is related to the parameter kappa in the passive scalar equation, perhaps. So you have a sequence of vector fields, maybe if they solve Navier-Stokes, but you want to take them in such a way that you have roughness, like you're in the turbulent. You know, they're looking like a turbulent fluid. This seems very hard though, because as we've seen, it's very hard to understand what's going on in those equations. And so we're just going to try now to build a vector field that looks as much like a fluid can look as possible. So we don't want it, so we want it to be kind of looking statistically stationary. We want it to be continuous in space and time and not have jumps and things like this. Okay, and we would like, of course, to see that it has this diffusion anomaly. The Kolmogorov theory of turbulence says that the vector field should look like a kind of fractal. And so maybe we can make a vector field that looks like a fractal and has all the active scales that you would imagine at one time, and doesn't just like have, like that checkerboard example, have sort of action on one scale for, you know, until time 1/2, and then in the next 1/4 time interval have action on a different scale, but actually has a fractal sort of built in. Okay, I think I'll skip this slide because it's maybe a level of detail that I don't want to get into, but I'm trying to discuss the regularity of what Holder regularity for the scalar you should expect. And if you're interested in that, you can go back and look at that slide. So here's the theorem that we prove with Vlad Vicol. We take a parameter beta, which is less than 1/3. We can't go above 1/3 with our method, but so we can't go all the way up to exponent 1, like in the other papers. However, 1/3 is kind of the physical exponent for what you expect from the fluid. And we take a parameter alpha, which is the expected Holder regularity that you would have for the scalar. Then we can build an incompressible vector field, so it's divergence-free. It is C beta in space and C beta in time. So it's, you know, it's continuous in it's basically L infinity in time into C0 beta in space, and L infinity, you know, it's C0 beta in space into L infinity in time. Okay, so there is a vector field. There is a sequence of kappas going to 0. So not the full sequence, but we have some subsequence of kappas going to 0, such that for every initial data, which is mean 0, if you look at the solution kappa of this equation, then along that sequence, the dissipation of scalar variance is bounded below. I guess I didn't say what rho was. Anyway, there exists a rho positive. So it's bounded below. And the scalars have the expected Holder regularity that you would expect them to have, which I haven't really explained, but we have that too. Okay. So this is the theorem statement. And I need to say more about what the vector field looks like for it to be. So there are other statements that you can make that make this a more convincing statement. But let me talk about what the vector field sort of looks like. Okay, I should say that this is in 2D, but again, 2D is the harder case because in higher dimensions you somehow have more room and the topology is less stressful. You know, there's less constraints to the topology. We work in 2D because it's nice to work in 2D because of the vector calculus is easy, right? You have grad perp and things like that. Anyway, the vector field B has a fractal structure. And we build it by hand. Okay, in some sense, at leading order, it solves the Euler equation. Like it's trying to solve the Euler equation, but because we're building it by hand, we're going to make errors. But it's at sort of leading order, it does. The sequence is explicit and does not depend on the solution. That was in the theorem statement, but I wanted to underline that. The reason that we have a sequence and not the full, like just any sequence of kappas going to 0, is because when we build the scales, the active scales into our vector field, we need to sort of make the scales separate more and more and more as you go down. Okay, and the sequence kappas, or the kappas, have to be kind of adapted to that sequence. It's like this kappa basically corresponds to an active scale in the vector field. And if you choose a kappa that's sort of between two scales in the vector field, then we don't know what happens. I'll explain that, and I'll try to explain that. The scalar has a fractal structure as well, which is kind of emerging from our proof. And the smallest active scale that you'd get, that you'd expect, is kappa to the 1 over 1 plus beta, which if beta is going to 1/3, just let's set beta equal to 1/3, is kappa 3/4, which is what you'd expect from the, that's what you expect the inertial scale to, the edge of the inertial range in the Kolmogorov theory. There are other important scalings that are predicted in turbulence theory that emerge, because a lot of these things are just scalings. But anyway, that is to say, the vector field we build looks physical enough that you get a lot of scalings that you expect from turbulence. So some comments on the proof before I kind of try to explain the basic ideas in the proof, because in some sense the proof is more interesting than the theorem, I think, in this case. We do not prove the theorem by studying mixing properties. So we do not think of the vector field as pushing around particles until in 1 minute the diffusion smears it out. So we don't try to treat the Laplacian like a perturbation term until the very, very end when it dissipates things. We're going to study the equation, and at every scale, the amount of Laplacian that we have is going to be sort of order 1 on that scale, as we're going to find out. Okay, so what we're going to do is we're going to analyze, we're going to zoom into the smallest scale. And when you zoom into the smallest scale and you sort of, blow it up, what you find is that the Laplacian term and the drift term are balanced, right? Because otherwise you would have zoomed in too far or not enough. So they're in balance. And we're going to look at that scale, and we're going to see, but there's a Laplacian, and there's a vector field which is stirring things. And the effect of that stirring is to enhance the diffusivity. There's enhancement, which means that when you go to a larger scale, you should have a larger effective diffusivity. So you kind of replace the wiggles in the vector field at the smallest scale and put them into the Laplacian, and the Laplacian gets bigger. And then it gets bigger just in time to greet the next scale of the vector field. And then you look at that scale, you see wiggles in the vector field, which is seeing a renormalized Laplacian, which are in perfect balance. And again, you have the same pattern repeat. So you have enhancement of diffusion until you go to the next higher scale. And so you do this arbitrarily many times. And somehow the vector field is putting its wiggles into the Laplacian in some sort of renormalized sense. So this idea, when we thought of it, we thought we were very smart. And we had a very original idea, and it turns out that the idea was, we were scooped slightly by 150 years, because the idea goes back to Boussinesq in the 19th century, who basically said the same thing. I don't even think they had the notation to really say the idea, but they had the intuition before they had even barely invented calculus. And, I guess they had calculus, but not with our current our current notation. Anyway, I found the right term to Google after a long time. It turns out you should Google eddy viscosity, or eddy diffusivity, or eddy viscosity. And this is what they call this idea in the fluids literature. And if you open the book of Landau and Lifshitz, and you look at their derivation of Kolmogorov's theory of turbulence, they actually use this to derive it. Okay, so we're going to try to make this rigorous using ideas from homogenization theory. Okay, so here's again sort of the cartoon of the proof. Okay, so these things are in log scale. Okay, so here are the scales. I'm going to make a sequence of scales. Epsilon 0 is set equal to 1. There's going to be epsilon 1, which is like 1 over 1,000, or some very small number. I need to separate them quite a bit. Then epsilon 2 is 1 over 1,000 squared. Epsilon 3, and I'm going to keep making them smaller. Now, actually, I need the aspect, or the ratio between two epsilons to grow slowly as the epsilons get small. So that epsilon m, if you look down here in very small, there's a small disclaimer. Epsilon m plus 1 is like epsilon m times a small number, which is proportional to epsilon m to a positive power. So this actually means that the scales are super geometrically going to 0. But it's close in some sense to being geometric. But we need them to be super geometric in order to make our proof work currently. Anyway, the smallest scale that you find is kappa to the 3/4. Because if you went to a smaller scale, the diffusion would kill everything and you would have no drift, okay? And it would be completely boring. So you should first look at the scale kappa to the 3/4. And you go there and you find that the diffusivity is kappa because the vector field hasn't done anything yet. And then what you do is you homogenize the wiggles in that vector field. You zoom out and you kind of erase the wiggles in that vector field. You forget them. But in order to forget them, you need to replace the Laplacian term with the effective the new effective Laplacian term, and it grows a little bit. And if you plot it log against log, it'll be a straight line, okay, with slope of 4/3, because the diffusivity at a particular scale is epsilon to the 4/3, okay, and that's sort of the Richardson 4/3 law. It's not really 4/3; it's 1 plus beta or something like that. But beta is going. If you think beta is a number very close to 1/3, then it's essentially 4/3. And the idea is that once you renormalize one scale at a time, there's an arbitrarily large number of scales as kappa goes to 0, but no matter where you start, you get on this little escalator and you go straight up, and by the time you get to the top, it's of order 1. So you're basically essentially the same as the heat equation. And we know that the heat equation has diffusivity, right? It's not even anomalous. So the anomaly is that you get to ride this escalator. Okay, so that's sort of the cartoon of the proof. And maybe I'll pause and see if there's anyone that wants to have a comment or a question. I feel like does anyone want to ask a question?
Yeah, can I ask a question? So
yeah,
why does this magic number 1/3 comes into the theory? So this 1/3 corresponds to the precise scaling that you expect in turbulence. So
yes.
did
So
you
we see it in our proof as okay. So why do we see it in our proof? We see it in our proof because we're making the fluid, or sorry, we're making our vector field look too much like a fluid. So it's going to have the fluid scaling. That's a very high level explanation. The low level explanation is that if you look at our fractal construction and you look at what we need to close the estimates, we get a constraint on the exponent beta, and the constraint is exactly that it be less than 1/3.
Good. So
okay.
The second explanation means that mathematics knows this 1/3.
Yes. Yes. Somehow. I think that it's so, I'm ignorant enough that when I went to do this, I knew that there was a 1/3 round, in fluids. Okay. So I'm not completely stupid, but when Vlad and I were computing this, we were just doing the calculation. We got the 1/3, and then I thought, maybe this is supposed to be like that. But it's not. We didn't get it on purpose. It comes from the proof, and we can't do better. I mean, we've tried for a long time.
Interesting.
So we can't do better. Okay. I think to do better, actually, you have to start breaking the regularity in time. Somehow, because our vector field looks like a fluid, the time regularity and the space regularity are kind of the same exponent. And if you want to go beyond 1/3, I think you have to start to do things that are rougher in time, which our method doesn't really allow, as I'll explain in a second. Okay, so the point is, I think I've already said this now, at every length scale, the effective renormalized diffusivity is basically in balance with the advection term. And so what you see is an advection-diffusion equation at every scale. You never see, if you've renormalized correctly and you're thinking about the problem in the right way, you never see a transport equation perturbed by a tiny diffusion term. You always see, you see the same thing at every scale, in fact, right? It's a fractal. So the idea is that we're going to take this equation. So here, this is how the proof works, literally. We take this equation, we denote by theta m the solution of the equation where I take the vector field B and I just rub out the scales that are rougher than epsilon m. Remember, I have the sequence of active scales. All the scales that are smaller than epsilon m, I mollify them away. I just mollify with a mollifier on a scale in between epsilon m and epsilon m plus 1 or something. I just kill the epsilon m terms, or m plus 1 and beyond. And then now this is a smooth vector field. I can solve the equation. And then I'm just going to homogenize one scale. I'm going to say that it homogenizes to this equation where I have erased the very smallest scale that is still left. And this number kappa gets bigger because for smaller m, or smaller m are closer to the macro scale. Like big M is small scale. So I go to a bigger scale and I get a bigger kappa. Okay, and that's how the proof is going to work. Okay, now the problem is that you have to do, the reason this is hard is because in homogenization theory, usually there's only two scales, not infinitely many. And usually the scales are becoming asymptotically well separated. In our problem, they're not becoming asymptotically well separated, right? They're just scales that are there, and they're not being stretched by some parameter going to infinity or something. They're just there. And there's infinitely many. So that's sort of the thing that makes this hard. Otherwise, this is kind of a classical homogenization problem. If you imagine that you have some limit of scale separation. Okay, and that's the reason why this problem was maybe studied in the 90s, but they didn't prove our theorem, even though they were trying to. It's because that it's this issue with the scale separation. Anyway, let me talk about how the homogenization is actually going to work. So let's step back and just imagine now that we have some vector field, which is periodic in space and time and incompressible. Because it's incompressible, there's a skew symmetric matrix. It's like the matrix potential for the solenoidal field. Like, you have a magnetic field, you have a matrix or a vector. I mean, in 3D, you would write this as the curl of a vector field. In 2D, you would write it as grad perp. But in dimension D, you have a skew symmetric matrix such that the divergence of the skew symmetric matrix, meaning you contract the I index, you do partial xi, sij, sum over I. That makes a vector field, which due to the skew symmetry is automatically divergence-free, and any divergence-free field can be written like this, okay? So you can write this advection term as the divergence of S, the matrix, times the gradients of theta, because when the divergence hits this, it makes a Hessian, which contracts against the skew symmetric, makes 0. Okay, so then you only have the divergence hitting the S, which makes the B. So the point is you can write this advection term as kind of a second order term, but you have to work with now an elliptic matrix, which is not symmetric. Excuse me. Okay, but we know how to do that in elliptic homogenization theory. We don't care that the matrix is not symmetric. And written in this way, it nicely fits into the theory of homogenization. So we want to understand solutions of a parabolic equation with a skew symmetric matrix on very large length scales, on length scales that are much larger than the wiggles in this vector field B, okay? And what you find is that basic homogenization theory says, kind of homogenization theory 101, says that this will, in the large scale limit to this operator, where this operator now, here it depended on space and time, here it's constant, it's A bar, where A bar is the effective diffusivity matrix. And the point is that by an easy calculation, you can show the A bar will, all of its eigenvalues will be at least as big as the symmetric part of the A. Okay, adding the skew symmetry can only enhance the diffusion because it's an advection term, and if you stir your coffee, the milk will get mixed faster. And so this is called enhancement. The effective diffusivity will get larger due to the stirring. And so you can just sort of replace this with that at larger scales. The question for us is, how large do you need to make the scale separation in order to see that that's basically happening? Do we have enough room? Because we have a lot of scales that we need to put in, and we need to know that we have room to do it. But this is the idea that we're going to use. Okay, so let me give you some examples of this in practice. I'm going to try to speed up a little bit, otherwise I won't get to all the punchline. If you have a cellular flow, so the fluid looks like this, okay, the advection term. The diffusion matrix looks like this: kappa kappa on the diagonal, minus phi phi, where phi is the grad, sorry, B is the grad perp of phi. So phi is the stream function for your vector field. And so if you're in 2D, basically the skew symmetric matrix, right? There's only one entry essentially, and it's the stream function, because in 2D you have a stream function. So anyway, this will homogenize to A bar, which is a multiple of the identity. And this C, the special C, which depends on kappa, is actually square root of kappa up to a constant. And this is what these authors showed a long time ago. So kappa becomes square root of kappa. So that's a lot of enhancement. You go from kappa to square root of kappa. It's a big jump. Okay. A shear flow will potentially make an even bigger jump. Again, I'm in 2D. My stream function is super simple. It's just sine. Okay. This is a vertical shear. It's going up here, down here. So this thing, if you have kappa, and here the length scale is epsilon. So I want the distance, between, I want the period to be epsilon here. And I want to put the parameters here so that the Lipschitz norm of my vector field is rho. Okay, so rho is like the strength of anyway, it's the Lipschitz norm of the vector field. The A bar will be kappa in the horizontal direction, because the vector field doesn't really do anything to the horizontal component. But in the vertical component, you have a gigantic jump. You go from kappa to something which is 1 over kappa. So as kappa gets smaller, the amount of enhancement gets bigger, which is kind of weird. And it's proportional to the period to the fourth, and then this parameter rho squared. Okay. If you alternate these in time, so you have it going up and then left, right, up, down, left, right in time, the alternations in time will just average. And so you'll average this matrix with the diagonal entries transposed, and you'll get this. Okay. They'll each get kappa, but you'll have half of this in each. And okay, so that's what will happen for a alternating sort of very simple shear. Okay, so now what is the reason that this is happening? Why is it proportional to 1 over kappa? You can think about it very, very simply. Like, imagine that you put a particle in that vector field with a very small amount of diffusion. It'll just go up or down depending on its horizontal position. And it may go up for a very long time if the diffusion is small. Eventually, the horizontal diffusion will move it into the other kind of channel. Like you imagine it's on a highway and its horizontal position is diffusing. Eventually, it'll diffuse across to the other side of the highway, so it'll have to go in the other direction. And you'll have this random walk where it makes very big jumps in its vertical position due to that. And if you think about this from a random walk perspective, you can kind of sort of ballpark, or you can make an approximate guess as to what the diffusivity will be. And I won't go through it because I'm running out of time, but you would guess the correct answer, what I put back there. What I put back there is this thing here is exact because it's computed from PDE, just exact calculations, which are easy because this is a very explicit function. Okay. Anyway, but you can guess it from like just thinking about how the particle would move around. So the alternating in time shear flow acts like a diffusion with this amount of diffusivity. The new diffusivity on the larger scale is proportional to the old diffusivity times this constant. Okay. Now, if you think about how far you have to zoom out before you start to see the random walk look like a Brownian motion, because if you haven't zoomed out until this sort of, the particle has time to move once into the opposing direction, then you won't see any effect at all. But if you zoom out on length scales and time scales larger than that, much larger than that, then you will see kind of a random walk, which will start to look like a diffusion. And that's the length scale on which homogenization should happen. And if you think about it, then you get these length scales for the spatial scale and the time scale. Okay. And so we need our scale separation. We need that the next scale we put into the vector field be larger than this, so that there's room to homogenize before you see the new wiggles appear. And that's kind of the constraint on our construction, which forces it to, not work for beta beyond 1/3. Okay. So the idea then is very simple. You just want to take the thing that I just described for the alternating shear, and you want to make that happen on a sequence of scales so that you get a recurrence relation, so that you get, let me see if I can go back, that this becomes a kind of recurrence relation between two scales. Okay, so you want to just make a machine that does this over and over again. So we make an infinite sequence of scales, and we make the vector field oscillate kind of on those scales. Scales below kappa to the minus, actually, this is not right. It should be minus. It should be kappa to the positive 3/4, not minus 1/2. I don't know what I was writing there. But scales below kappa to the 3/4 do not matter. So there is some smallest active scale. So you'll for every kappa, you'll start with this. You'll have a finite sequence of epsilons. It's just that as kappa goes to 0, you have, more and more and more scales. And the idea is we try to homogenize this operator, where there's an n here, epsilon n. and we try to make it look like this new operator where this kappa has been replaced by this with n-1. Okay, and then we try to iterate that. So for the first scale, we go from kappa to kappa bar n, some effective diffusivity. And then we iterate and we try to show that kappa bar m+1 times Laplacian plus the vector field with m scales goes to minus kappa bar m, where I delete the last scale. And you try to iterate that. And you try to show that at every scale, what you see is this simple shear flow construction. Okay. So anyway, here's a slide that kind of describes what I just tried to say. We try to do it so that this thing becomes the recurrence relation, which comes from that analysis of those two scales interacting. And in order for this to work, you have a bunch of constraints that you need. Like here's a constraint that says that the next larger scale must be much, much larger than the scale at which the previous one homogenizes, because otherwise the scales interact in a way you can't control. So this is not a fact, this is a requirement. And so in order to make the requirement hold, that's why you need beta less than a third. Okay, so anyway, this is the idea. There's one more idea that I want to explain. Yeah, so let me skip this one. So I want to explain the idea of how you actually build the vector field now, okay? And because there's one more interesting part to it, that there's one more twist to the story, which says that you have to make, if you weren't trying to before, you have to make your vector field look like a fluid in an important way, in a way that the other models like the Krykman model and so on do not satisfy. So I think that this is sort of in some sense maybe physically interesting. So your first idea to make the vector field is that you're going to take those alternating shear flows that I described, which now I denote by UML. Okay, so I'm going to sum. So I think M is the scale of the shear. It's been scaled. And I'm going to alternate them in time between basically even and odd. And so the L is just cycling between the parity, basically even odd. So like when L is even on those time intervals, I have them in the x direction and otherwise in the y direction. And I make these things be cutoff functions of time. So you see they look like this. They kind of add to 1, but the cutoff functions are sort of are making the vertical and horizontal shears turn on and off. This is essentially the first idea. Okay, you want to just add the shears together. Okay, this does not work. This will not work. It will not work because if you want to make your thing Holder continuous, then obviously the amplitudes associated to smaller scales must be smaller, right? A continuous function has, smaller wavelengths, higher frequencies have smaller amplitudes. Otherwise, it's not continuous. And so what that means is that the low frequency modes, from the point of view of the small scales, are like a very large sort of constant background drift. If you zoom into a small scale, the effect of the larger scales is just to give you a very large constant background drift. And that constant background drift will destroy the enhancement due to the shear. Because the whole reason that the shear was enhancing is that it was staying on these highways where it's like being sheared for a very long time. And if you want, the streamlines are very long. But if you add a constant background drift, it destroys that. And so you don't actually have enhancement, nothing works. So then you think, okay, well, this is not going to work. I don't know how to do it. Well, what you have to do is you have to use the same idea, but when you put the small scales into your vector field, you have to put them in the coordinates of a particle who's being advected by the scales you've already put. In other words, you make an iterative construction, and each scale that you want to put in, you first put the largest scales in, then you put the smaller ones after. And when you get to a scale and you want to insert it into your vector field, you put it in the Lagrangian coordinates of the flow of the previous vector field. So you look at a particle flowing down the river of the previous scales, and you put your shear flows to be in those coordinates. And then you will not have any interaction, because if you switch to Lagrangian coordinates, you'll think the background drift is 0. And so that's the reason that it works. And so that's what we do. transport the shears by the background flow. So this is, and the need to do this makes our proof tremendously more difficult, because the complexity of having to compose everything with the Lagrangian flow maps, it causes kind of non-trivial corrections to the effective equations and to the homogenization problem. One interesting note is that real fluids do that, right? Real fluids have the property that high frequencies in the fluid are advected by the low frequencies. In fact, the U dot nobla U term in Navier-Stokes is saying basically that the velocity field advects itself. So that's actually a property of real fluids, and it's a thing that we kind of stumbled on to make our proof work. Like, we had to make it look like a fluid. Okay, I have more slides, but I'm running out of time. Most of my slides are about why the proof is technically hard and how we had to fix it, and how the proof is working. Maybe I'll just go over them so people that are watching this video later can look at the slides. But I put this slide because I was flipping through this book by Uriel Frisch when I was educating myself about turbulence, which is a wonderful book. And I stumbled on this section. This is back when we thought we had a very smart original idea, and he has a section, a very old idea, which I thought was very funny. So, and it explains how this idea goes back to the 1850s. But then Frisch explains that this can never work in a rigorous way because there's no scale separation, and therefore it's best regarded as a pedagogical advice, or a pedagogical device, this eddy diffusivity. So I think the upshot of our work is that you can maybe make this actually work. At least we kind of build a sort of synthetic vector field, which sort of looks like a fluid, maybe, for which you can prove something. And so maybe there's some hope that an idea like this can work. So I will stop there and take your questions. Thanks a lot for listening.
Oh, thank you very much, Scott, for the very clear and very nice presentation. We have time for some questions. If you have any questions, please feel free to unmute yourself and just ask them. All right, then maybe I'll venture a question if there are no others. You mentioned several times that things are expected to get harder as the dimension gets lower, and yet you're working in 2 dimensions.
Yes.
Can you be a little more specific on?
Yeah, so our proof works as such in dimension D. So you just it's like we used 2 dimensions because we wanted to write grad perp, and we wanted to deal with stream functions and not have like indices Sij all over the place, because it's just the stream matrix becomes scalar, and it's just the notation becomes easier and more familiar to people. But everything is fine. Yeah, there's absolutely no issue with making it work in higher D. It would effectively be very boring to, you would just, there's not a single a lemma that it would be more difficult. Higher D is usually easier because it's easier to make vector fields do weird things in higher dimensions, because the streamlines can tie themselves in knots and do all kinds of stuff. The topology doesn't constrain you. So there's it's true. Yeah, you see this in the literature for mixing. So there's all these papers by people studying mixing of vector fields and transport equation. And in 2D, there's just more rigidity. It's harder to make weird examples in 2D.
And is there any idea of, because there still are a number of open problems as far as I understood, is there any idea of trying to address those open problems maybe in very high dimension first to make things easier, or does that not really make
That's
things
an interesting idea. That's an interesting idea. I don't know. I think that, so I should say, I didn't say this, this theorem that I stated, it's like half of it is on the archive and the other half is we're still finishing. So we proved the anomalous diffusion. We didn't prove the Holder regularity. It's still being written. It's taking forever to finish it. if I were to want to work on this, I would want to finish that paper. But assuming that paper's done, and I wanted to extend and do this better, I would probably try to make. I would love to have an example that would be random instead of using periodic deterministic ingredients. That would be great. I don't know how to do that because the homogenization estimates that I need in the random case are not true. I mean, I don't know how to prove things like that in the random case because the homogenization theory becomes much more complicated. I think I would also like to make the scale separation geometric all the way down because that's more physical. And it's hard in an interesting way mathematically. And I think that would be a very good thing to do because that makes it, if you can prove it for geometric scales, you're somehow closer to a true fractal and closer to what should be the physics. Of course, then you want to know, it's kind of a separate question in some sense. Why do the solutions of the fluid equations do that? And, why do, because in some sense, our work is about taking the wiggles in the vector field and showing that, yes, the scalar gets wiggles too, all the way down the scales. But it seems like it's not exactly the same question of how does the solution of Navier-Stokes get the wiggles, because it's like a chicken and egg issue, right? It's like it has wiggles, so it gets more wiggles. So and it's much harder to understand what's happening. Of course, I would want to understand that, but I think that's not. I'm not going out on a limb there. I think everyone else wants to understand that too, and nobody knows what to do. So that's. I don't know if I gave a complete answer to your question, but
yeah, definitely. Thank you. Are there any further questions?
Yes. So you first introduced this shear flow as an example, but it seems like it was rather essential for your construction. So
yeah, so we used the shear flow as like the base of our fractal, right? It's like the repeating pattern of shear flow. I think that you could use other things, but you would need the shear flow is doing a lot of enhancement. In some sense, a lot of other examples that are not shear flows, if you look closely, I think they kind of are shear flows. It's like the cellular flow, nothing's happening in the middle of the cell, but then on the edges of the cell, that's where all the diffusion enhancement happens, and it's kind of shearing there. So in some sense, it's like you can use something that's not a shear flow as long as it has some shears in it enough that it, but we had to kind of use a full, like almost a full dimension amount of shears. Like the Hausdorff dimension of the active, space-time coordinates is like almost d+1 dimensional. And we had to do that in order to get close to beta is 1/3. It would be interesting to see, a real fluid is not doing a back and forth with shears. It would be interesting to see what you really need to make the proof work. And we use the shears because at a certain point, we need to do some exact calculations to go from one scale to the next in order to close our, this thing was fairly hard to formalize, as you could imagine. And so we use the shear flows because they're more convenient.
Yeah. So a historical question is that, so did they use shear? Probably they used eddy or something in the old works.
I don't
know.
Which old works, like Andy Maida and Marco Amavellaneda?
Mimi, I was talking about these historical works, which is on this book. Eddy, you said this idea is called eddy viscosity.
Yes, but they're really they're giving a purely heuristic argument.
Okay.
So the argument is like it's a typical like of this like phenomenological argument where you don't write down. I don't know. It's let's put it like this. It's not it makes me uncomfortable to read it, but I think there's a lot of wisdom there. But it's not a math argument. It's a kind of very vague argument. So if you look in the book of Landau and Lifshitz, like you can see it, and that's why he calls it at best a pedagogical device, because basically he says you can't formalize this. There's no clear separation of scales. So, and he explains that there is a math theory called homogenization theory, and you can do stuff, but you only have two scales, and they're asymptotically well separated. So you can kind of wave your hands, and then he also says that in attempt to make this more of a physics, more not rigorous, but more like a physics argument is given by renormalization group.
Mhm.
But renormalization group is kind of what we're doing. We just call it homogenization, right? We have effective diffusion at every scale. It is renormalization group. So we're sort of, if you want, trying to use this sort of PDE machinery or what have you, this perspective to make rigorous, for this example, the kind of renormalization group argument that you'd want to use. Yeah.
Thank you.
All right, well, thank you so much, Scott, and thank you everyone for attending. We hope that you'll join us again in 2 weeks when we'll have a talk by Marius Lem, and yeah, we hope to see you all there.
Thanks.
Okay, I stopped the recording.